In this lesson, we'll be taking a look at electric potential using the positive and negative signs. First of all, what is electric potential? The definition of electric potential is electric potential energy per unit charge at a point in space. The symbol for electric potential is a capital V, and the equation is basically the definition. So electric potential energy divided by the amount of charge that has that amount of electric potential energy. It's important with this equation to put in the signs for all the quantities. So we'll talk in a moment about what sign the potential has, but you need to put in the signs for the potential, the electric potential energy, and the charge. What is the electric potential at the negative plate? At the negative plate, the position D is 0. We will always set up our coordinate system that way, so D will always be 0 at the negative plate. Because of that, the electric potential energy will always be 0 at the negative plate. You can see the equation there for electric potential energy is negative Q times E times D. So when you substitute 0 for D, you end up with 0 for the electric potential energy. As a result, the electric potential is also 0 at the negative plate. So the key idea here is that the electric potential is always 0 at the negative plate. What is the sign of the electric potential at positions between the plates? So anywhere not at the negative plate. Well, let's take a look at what happens in our equation if the charge Q is positive. If the charge Q is positive, then the electric potential energy of that charge anywhere between the plates will be a positive number. We looked at that in a previous lesson. Then divided by the charge, which is positive, you have a positive divided by a positive, which gives you a positive number for the potential. Well, what if Q is negative? If Q is negative, the electric potential energy of that charge will be negative. The charge also will be negative. When you take a negative and divide by another negative, you get a positive number. So from this we can conclude that everywhere between the plates and at the positive plate, the electric potential has a positive value. So at the negative plate it's 0, everywhere else it will be a positive number. Let's look at an example. We have two parallel plates with opposite charges. The electric field is 100 newtons per coulomb. The distance between the plates is 4 meters, and the two charges are given. One is positive and one is negative. What is the electric potential energy of each charge when it is 1 meter from the negative plate? So when we get to part B, we're going to be calculating the electric potential, but we can't calculate electric potential unless we first know electric potential energy. So that's the purpose of this part. For Q1, the electric potential energy, using the equation negative Q times E times D, comes out to be positive 200 joules. Just a reminder, you do have to put in the signs for the electric field, the charge, and the position. For Q2, we now need to put in a negative for the charge, so negative 4 coulombs, but the other values are the same, and we get negative 400 joules. So when we put different charges at this same point, which is marked by a black dot in the picture, so first we're going to put Q1 there and we find that it has 200 joules of electric potential energy. Then we take that charge away and we put Q2 there and we find that it has negative 400 joules of electric potential energy. So same spot, but different amounts of electric potential energy. Let's take a look at electric potential at that spot. What would the electric potential be? Well, let's calculate it using Q1, our positive charge. We need to divide the electric potential energy by the charge using the electric potential energy that we calculated on the previous slide, which was 200 joules. We get 100 joules per coulomb for the electric potential. And I should have added one more line there, which would just replace the joules per coulomb with a volt. A joule per coulomb is equal to a volt, which is the more commonly used unit for electric potential. Using Q2, we now need to substitute our negative 400 joules and then divide by our negative charge. And so you can see that the potential comes out to be 100 joules per coulomb, which is equal to 100 volts. So we can see that no matter what the charge, we have only one value that we always get for the electric potential at this point. So it doesn't matter what charge you put at this point. The electric potential will always come out to be 100 volts. Now that's really useful because it's a value that depends on this position, not on what you're putting there. To conclude, the electric potential at a point in space is independent of the charge placed at that point. The definition of electric potential is here. This is one of our main equations. Now, applying that equation to parallel plates, we can substitute the expression for electric potential energy, and we find that the Q's cancel out. And this is why the electric potential is independent of how much charge you put there, because the Q, the charge, cancels out. When the charge cancels out, we're left with this expression. Electric potential is related to the electric field and the position D between the plates. This is going to be another primary equation we're going to use. So we'll have two equations for potential. One that has to do with the electric potential energy per unit charge, and one that relates potential to electric field and position. That one's just for parallel plates. The electric potential at points between two parallel plates is determined by the electric field between the plates, and remember that the electric field is always negative, and the position D of the point between the plates, and D is always positive. So once again, you can see that the potential, electric potential, is always going to come out to be a positive number. Let's take a look at another example. Actually, this is the same example, but we're going to use our new equation. What is the electric potential at a distance of 1 meter from the negative plate? So there's two ways you could approach this. We could find the electric potential energy for a charge and then divide by the charge. And that's what we already did in parts A and B of this example. Or we can use the electric field and the position between the plates. So we're going to follow that approach now and apply this new equation. So using our equation, we need to put in negative 100 newtons per coulomb for the electric field, and the position is positive 1 meter, and we come out with 100 newton meters per coulomb. You might remember that a newton meter is a joule, and a joule per coulomb is a volt. So once again, we get 100 volts. Are there other points that have an electric potential of 100 joules per coulomb or 100 volts? Yes, every point on the dashed line at position equals 1 meter. Every point on that line will have a potential of 100 volts. And that's because when you look at your equation here for potential, all it depends on is the position. And every point along that line has a position of 1 meter. Now let's find the electric potential at points A, B, and C. Well, they all have the same position, a position of 2 meters. So they're all going to have the same value for potential. And using our equation, we find that that value is 200 joules per coulomb, or 200 volts. And so over here, this dashed line, everywhere along that line, every point on that line has an electric potential of 200 volts. A line or curve composed of points that all have the same value for electric potential is called an equipotential line, or an equipotential. So these dashed lines that are drawn here, these are equipotentials. Example, the electric potential at position of 2 meters is 200 volts. Find the electric potential energy of a negative 6 coulomb charge placed at that point. I highly recommend listing variables. It will help you get clear on what quantities you already know and what quantities you're looking for, and it'll help you choose which formula you'll want to apply. So these are the given variables and what we're looking for. These are our equations that we have to work with. So we want to find electric potential energy, and we don't know the electric field, so this is not going to be useful. And also this one would not be useful. which leaves us with this one, and that one's going to be the one to use. So using this equation, we can substitute our given values, multiply both sides by -6 coulombs, and find the answer. -1200 joules is the electric potential energy. And this makes sense because a negative charge should have a negative electric potential energy. How do we find change in potential? Well, the electric potential at some point is given by this first equation. The change in electric potential between 2 points is very similar. The only difference is now we have change in potential and change in electric potential energy in the equation. Change in electric potential is often called potential difference. So be aware of the different language used there for that quantity delta V. It's important to identify your initial and final points when working with an equation that involves a change, because a change is a final value minus an initial value. Here's an example. What is the potential difference if you go from A to B? Okay, so it's the change between those 2 points. So the final potential is 0. The initial potential is 400, so we need 0 minus 400. So the potential difference, or change in potential, is -400 volts. And notice that, one more example, a -3 coulomb charge moves through a potential difference of 1000 volts. What is its change in electric potential energy? And you might want to pause the video and try this one on your own and then continue when you're ready. Listing variables, I have my charge, my potential difference, and I'm looking for electric potential energy. This is an equation that will allow me to find that. And actually there's a mistake right here. This should be change in electric potential energy. There should be a delta here. Now substituting our values, we have this. And our result is -3000 joules. The general definitions for potential and change of potential are on the left. As we apply those general definitions to parallel plates, we get the expressions on the right. Example, 2 parallel plates are 4 meters apart. The electric field between the plates is 100 newtons per coulomb. What is the potential difference between the plates? The first step is choose initial and final positions. It looks like it's really only asking for a magnitude because it doesn't say what the initial and the final positions are. But to be consistent, it would be good to choose an initial and a final position. So I'm going to choose the positive plate as my initial position and the negative plate as my final position. Listing my variables, my displacement will be negative because it's going to the right, which is opposite the direction of the positive d-axis. Electric field is always negative, and we're looking for change in potential. Substituting our values, we have -400 joules per coulomb, or volt. So the potential difference between the plates, the magnitude, would just be 400 volts. In summary, electric potential is the energy per unit charge at some point in space. Electric potential is a property of a point in space and does not depend on the amount of charge you put there. For parallel plates, the electric potential is determined by the strength of the electric field and the position of the point you're looking at between the plates. So V equals -E times D. And remember that electric potential always has a positive value between the plates.